Hello everyone, and welcome to another episode of Cabinet of Curiosities on our own devices. I'm Jean Messier, and today we're going to do something a little bit different and have a look at the remains of an unsuccessful research and development project. Now, a little while ago, I put out a video on a fragment of a CANDU nuclear reactor, which was part of a project I was involved in with Atomic Energy of Canada Limited shortly after graduating from university. Now, a lot of you seem to really like that video, and you asked for more content about my previous life as an engineer, and well, ask and ye shall receive. So the items I have with me here are all that remains of a personal project I undertook a couple of years ago to develop a magnetic eddy current delayed blowback system for self-loading firearms. Now, I realize there's a lot to unpack in that sentence, so please bear with me as I break it down. So, as most of you probably already know, a self-loading firearm is one which uses a portion of the energy from each shot fired to cycle the mechanism, or the action, and load a new round. Now, the action of a self-loading firearm needs to perform a number of functions in order for the whole system to work properly. So first, it needs to set off the cartridge. Second, it needs to extract and eject the spent cartridge casing. Third, it needs to reset the firing mechanism, whether that be a hammer or a striker. Fourth, it needs to strip a new round off the magazine, the belt, or whatever feed mechanism you're using, and chamber that round. And finally, and probably most importantly, the action needs to delay the opening of the bolt, the breech, until the chamber pressure has dropped to a safe level. And this is important because if the breech were to open immediately upon firing, a lot of hot, high-pressure gas would vent out of the action, and this is bad for a number of reasons. Number one, you're losing a lot of gas that would otherwise be used to propel the bullet down the barrel, so you're going to lose quite a bit of muzzle velocity. But probably more importantly for the user, that hot, high-pressure gas is going to vent directly into the shooter's face. And the bolt is going to be propelled rearward at such high velocity that it can easily damage the firearm and injure the shooter. So every self-loading firearm has some sort of mechanism to prevent the bolt from opening until the pressure has dropped off. Many different ways of doing this, but the two main categories are locked breech and delayed blowback. Now, a locked breech firearm is one in which there's some sort of mechanism to lock the bolt in place during the firing cycle, and there is another mechanism incorporating some sort of delay that doesn't let that bolt become unlocked until the chamber pressure has dropped. Now, one of the examples of this would be a recoil-operated firearm, like this Colt 1911. Now, the slide and the barrel of the 1911 are held together by a series of interlocking slots. So when you fire the pistol, the recoil of the cartridge is going to make the barrel and the slide recoil back together. Now, at a certain point, that barrel is going to start to rotate along a set of lugs, and it's going to tip backwards and unlock itself from the slide, thus unlocking the slide and allowing it to recoil fully, extracting the spent cartridge casing, resetting the hammer, and chambering a new round. Now, there's a couple of different ways of doing this. You can have tipping bolts, rotating bolts, flapper lock, all sorts of different mechanisms, but in the end, they all boil down to the barrel recoils, and the time it takes for the barrel to recoil to a certain point is what provides that delay. By the time it gets to that point, the bullet has already left the barrel and the chamber pressure has dropped. So another type of lock breech mechanism is a gas-operated system, such as in this MOS 49 rifle. Now, up near the muzzle here, we have a little hole, a gas port drilled into the barrel. And when the rifle is fired, once the bullet reaches that gas port, some of the gas behind it gets vented up through that port and into the gas system in the top of the rifle. Now, in something like an AK or an AR, you would have some sort of gas piston here between the gas port and the bolt. Here, this is a direct impingement system. So this is just a tube, and so the gas gets vented up, back, and blasts directly into the face of the bolt. But in both cases, that action unlocks the bolt and propels it rearward, allowing the whole mechanism to cycle. And so the delay here is induced by the distance between the chamber and the gas port. So by the time the bullet reaches the end here, it's about to leave the barrel and the pressure behind it is about to drop. And it's at that point that the rifle cycles. So as I mentioned before, the other major category of self-loading firearms actions are delayed blowback actions. And in these, there's actually no mechanism for locking the bolt in place, and other techniques are used to prevent the bolt from opening prematurely. So the simplest of these is what's known as simple blowback, such as in this Ruger 1022 rifle. And as you can see, there's no mechanism to lock this bolt in place. It's free to recoil on its recoil spring. And what delays its opening is the mass and inertia of the bolt itself. So according to Newton's second law, force equals mass times acceleration. So under an equal force, a larger mass will accelerate more slowly than a smaller mass. And the idea behind a simple blowback mechanism is you make the bolt massive enough so that by the time it gets moving and has moved far enough to open the breech, the bullet has already left the barrel and the pressure has already dropped. Now, this is very simple, it works quite well, but unfortunately, it's limited to relatively low power cartridges like 22 rimfire or pistol cartridges like 9mm or 45 ACP. And this is because larger rifle caliber cartridges are so powerful that in order to have enough of a delaying action, the bolt would have to be so massive as to be not feasible for a man-portable rifle. And so for these types of cartridges, a firearm has to have some other mechanism for delaying the opening of the bolt, such as rollers acting against a ramp or a lever that provides mechanical disadvantage. There's a whole bunch of different delayed blowback mechanisms, and you'll find these in firearms such as the Heckler & Koch G3 series, the MP5 submachine gun, or the French FAMAS assault rifle. So all this at last brings me to my failed research and development project. Because a couple of years ago, I came up with the idea of using magnetic eddy current braking as a novel delaying mechanism for blowback-operated firearms. Now, what is magnetic eddy current braking? Well, to demonstrate this phenomenon, I've come up with this very simple visual aid. This is just a piece of aluminum channel up at an angle. And as you probably know, aluminum is diamagnetic, meaning that magnets do not stick to it. Now, if I take an object about the size of a rare earth magnet, but non-magnetic, and slide it down the ramp, it travels at a particular speed. However, if I take a magnet of the same size and weight and slide it down, you'll notice that it slides very slowly. So what's going on here? After all, the magnet doesn't stick to the aluminum. Why is it being delayed? Well, the reason is, as the magnet travels down the aluminum ramp, it's inducing an electric current inside the aluminum. And that electric current is traveling in little loops called eddy currents. And those eddy currents, in turn, are generating their own magnetic field. And according to a physical principle called Lenz's law, the magnetic field generated by the eddy current will always be in opposition to the original magnetic field that generated it. And so there will be an opposing force that slows down the magnet. And this force is proportional to the speed of the magnet and the force at which it is applied. So the harder you push, or the faster it goes, the more resistance it encounters. And there's a number of different applications for this. One of the most well-known is in braking high-speed trains. So a lot of high-speed trains will have a braking rail and a set of electromagnets on board. And when the train wants to slow down, the electromagnet is energized and produces that eddy current braking force in the rail, and it essentially converts the train's kinetic energy into heat and slowly bleeds it off. And the advantage with that type of braking mechanism is it doesn't wear out because you don't actually have any surface-to-surface contact. And so it lasts a very long time and is very reliable. So because the eddy current braking force is directly proportional to the applied force, I thought this would be an ideal mechanism for delaying the opening of a rifle bolt, particularly because it would automatically adjust itself to the power of the cartridge. So it doesn't matter what cartridge you load, the higher the recoil force, the higher the opposing force, the two would always match. And there would also be a number of other advantages. For example, having a magnetic delayed blowback system would significantly reduce the cost of a firearm because this type of mechanism doesn't require a lot of precision machining compared to regular locked breech and delayed blowback mechanisms. It would actually be quite easy to machine and thus would reduce the cost of the firearm. And also, this type of mechanism would be very dust and fouling resistant. In a magnetic eddy current braking system, the parts don't need to be in intimate contact with one another. You can leave a little bit of a gap, and so it would be very forgiving of a little bit of fouling and thus be more reliable. So tons of different potential advantages. And because of this, I set out to find out whether I could actually take a magnetic eddy current braking system and miniaturize it to the point where it was compact, lightweight, but still powerful enough to be fitted in the receiver of a rifle. So in order to help me with this project, I teamed up with my good friend Siddharth Kedere, who you might remember from the episode of Real Engineering we did together a little while back on the movie Interstellar. Now, our first order of business was to create a computer simulation of a recoiling rifle bolt, specifically the bolt of this Ruger 1022 rifle. And we based that simulation on a number of different parameters. For example, the weight of the bolt, its range of travel, the rate of the recoil spring, and a number of assumptions we made about the ammunition. So for example, we assumed that all of the powder in the cartridge would burn up before the bullet separated from the cartridge casing. We're also able to look up the temperature of the burning powder, and by weighing the powder and assuming that it was all consumed and converted into a mixture of carbon dioxide and nitrogen, we're able to estimate the volume of propellant gas. And finally, assuming that the barrel is very heavy and that the firing cycle is very short, we assumed that the travel of the bullet down the barrel and the expansion of the gas behind it was essentially an adiabatic process. And putting all these things together, we're able to come up with a simulation that could output a displacement versus time and a velocity versus time graph of the bolt's motion. And we could tweak different things and add braking forces and other parameters in order to design our eddy current delaying systems. So in order to calibrate that computer model and later to test whatever mechanisms that we came up with, I came up with a test rig based on this rifle. So I clamped the rifle into a workbench. I set up a bullet trap in front of the muzzle, which was a steel sphere filled with sand and lead shot to catch the bullets and ensure that we could actually carry out these tests indoors, and set up a remote trigger mechanism with a small pneumatic cylinder, hose, a valve, and an air compressor. And I carried out a number of test shots using various types of ammunition and filmed the recoil of the bolt using a high-speed camera. And by looking at this frame by frame and comparing the acceleration profile of this bolt to our computer model, we were able to adjust both and see how they matched up. And lo and behold, they matched almost perfectly. Even though we had made a number of assumptions for parameters that we couldn't find good data on, turns out our assumptions were essentially correct, and the computer model almost exactly matched this rifle. So with that in hand, we moved on to studying the equations governing magnetic eddy current braking and trying to find out what sort of size and power of magnet we would need to have the proper delaying effect. So our first idea for creating a magnetic delaying mechanism was simply to mount permanent rare earth magnets in the bolt itself, and for our braking surface to simply use the aluminum alloy receiver of the rifle itself. So as the bolt traveled backwards, the magnet would drag along the inside surface of the receiver. It's already there, why not use it? But first, we had to cut down the bolt. And the idea here was to eliminate the bolt's ability to work in the simple blowback mode. It would be too light to actually delay the opening of the breech. And then by using magnets, we would be able to restore that delaying action. Now we managed to remove quite a bit of weight off this bolt, as you can see, compared to a regular 1022 bolt, but unfortunately not as much as we would have liked, because in many cases things like the firing pin or the extractor claw got in the way and we just couldn't remove that much material. And for example, in the bottom here, you can see we took out a large section of mass here, But unfortunately, when we loaded this bolt into the rifle, that pit tended to get caught on the fire control group and jam up the rifle. So we had to put a piece of high-density polyethylene in there and grind it smooth and to allow the bolt to actually function properly, but it did add a little bit of weight back. So we weren't able to eliminate the simple blowback action, but we were able to reduce it significantly enough that we could tell whether it had been restored by our magnets. Now, rather encouragingly, our initial calculations using our computer simulation revealed that restoring that delaying capability to the bolt would be a lot easier than either of us could have imagined, and would only require a magnet 12 millimeters in diameter and 2 millimeters thick. So we machined a counterbore in the top of the bolt, put the magnet in, loaded the bolt into the rifle, set it up on its test stand with the high-speed camera, and took a couple of test shots. And when we reviewed the footage afterwards, we found, well, nothing. The magnet had absolutely no effect whatsoever. And this got us scratching our heads a little bit because the results of our calculations were rather clear-cut. There should have been an immediate and very obvious effect. However, what we eventually realized is that the specific aluminum alloy that's used in the Ruger 1022 has a very low magnetic permittivity, so it's not very conducive to eddy current braking. So it was back to the drawing board. And what we ended up doing was machining out the top of the rifle receiver and machining a little block of copper, which is even better for eddy current braking than aluminum, that would fit inside and form a much better braking surface for our magnet. So with this in place, we loaded the bolt back in, we set up the rifle again, and did a couple of test shots. And once again, nothing. The magnet still had absolutely no effect, even with an ideal braking surface. So something was wrong, but we didn't quite know what. So rather than revising our calculations or doing more research or anything like that, we decided instead to take the Mythbusters approach and just try to supersize everything in the hopes of getting some sort of result. So rather than the little disc-shaped magnet that our calculations indicated would be sufficient, we loaded up the bolt with the largest, most powerful rare earth magnets we could get our hands on and remachined the copper drag block in order to fit those. And so we put all of this into the test stand, we fired a couple of test shots, reviewed the high-speed footage, and still nothing. Despite the fact that we had the biggest magnets and the biggest drag block and just the beefiest infrastructure that we could fit inside the 1022's receiver, it still had absolutely no effect on the recoil of the bolt. So it became clear to us that there was something that we were missing, that we need to do a little more digging to figure out what it was. And what we discovered was that magnetic eddy current braking is very sensitive to losses induced by the spreading out of the magnetic field lines as they emerge from the magnet. And as the field lines spread out, it reduces the density of the magnetic flux running through the drag material, and this reduces the efficiency of the braking process. Our research also revealed a potential technique for correcting this, which is called a magnetic yoke. And this is a C-shaped piece of iron that is used to hold the magnets, and this forces the magnetic field lines to travel in a circular pattern so that when they cross the gap between the two poles of the magnets, they travel in straight parallel lines. And this increases the flux density and increases the efficiency of the braking process. Now, at this point, we also realized that simply adding more and more magnets to an actual rifle bolt probably wasn't the way to go at this point. Our calculations and our real-world results just weren't matching up, and it would probably be better to gather some real-world data with which to actually design a functioning magnetic brake. So we sort of put the rifle aside for the moment and instead built this. And as you can see, this is a magnetic yoke. It's a C-shaped channel. We have a bunch of very powerful rare earth magnets on the inside, and then a drag block made of copper, which slides back and forth on this rod, which is all made of brass so that it doesn't actually interact with the magnetic field and interfere with the action of the brake. And of course, there's a little spring there to actually return the brake to its starting position. So in the interest of getting reliable and useful data, we opted not to test this braking mechanism using the impulse from an actual rifle, but rather to build a lower powered impulse system that was pneumatic. So we took the pneumatic system that we're using as our remote trigger mechanism in the rifle rig and used it instead to basically punch the piston on the end of the braking mechanism. And so we ran 3 sets of tests. First, just seeing what the actual acceleration profile of the piston was. Second, with the drag brake installed, but without its magnets installed, so we could account for the effects of friction and the return spring. And then third, with the magnets installed, so we could see what sort of braking force that we were getting. And once again, the answer was none. There was absolutely no detectable effect from adding the magnets. So it was then that it really hit us that there was a fundamental flaw with this idea from the very beginning. And that had to do with the extremely short distance over which a typical rifle bolt travels and the even shorter distance over which its travel must be delayed. Now, the mechanical components in something like a roller-delayed or lever-delayed blowback action act instantaneously once the cartridge is fired because they're transferring forces and the force transfer is essentially instantaneous. However, a magnetic eddy current braking system can only start providing an opposing force once it has reached a certain velocity. It needs to accelerate up to the point where it can actually start providing a force. And unfortunately, the acceleration of a rifle bolt is so extreme that by the time it has accelerated up to that velocity, where the magnetic eddy current braking system can actually start providing some sort of delaying force, it's already too late. The bolt has actually traveled back enough of a distance to allow the breech to open and the gas to vent out. So this type of mechanism is too slow. It doesn't have a fast enough reaction time to be used in this application. And because the process is so sensitive to factors like the spreading magnetic field and materials and things like that, it's not easily and reliably miniaturizable to fit inside a rifle receiver. So at this point, we abandoned the project. We realized it was just not feasible. But it was not in vain. It was a fun project to work on. It was an interesting project. It gave us some rather interesting results. And it also gave us some other ideas for spin-off technologies that we might examine in the future. So who knows, this project might bear fruit yet. So that's all I have for you today, a bit of a different one. I thought that it would be interesting to show you the entire thought process and the entire procedure behind an actual research and development project, albeit an ultimately unsuccessful one. And, that's the thing with research and development. Sometimes things don't work out, but you always learn things along the way. Anyway, I'll see you next time on another episode of Cabinet of Curiosities here on Our Own Devices. Until then, I'm Jean Messier. Have a great day.